let's continue. I'm very excited to introduce our next speaker, Manzil Zaheer. So Manzil recently joined Meta Gen AI Llama team as a research scientist leading LLM memory and personalization efforts. And previously, he was at Google DeepMind working on research and applications to Gemini Search and YouTube, while winning numerous awards, including Google Tech Impact Award. He received his PhD in machine learning from Carnegie Mellon University. And his research interest lies in developing intelligent systems that can utilize the vast amounts of information efficiently and faithfully. And he works on transformers, distributed optimization, and retrieval systems. And today we're going to hear this exciting talk on statistical perspectives on retrieval augmented models. So take it away, Manzil.
Yeah, thanks, Jim, for the introduction. And thanks for inviting me here. So I'm very excited to talk about some line of work we have been doing for a few years on understanding retrieval augmented models, more from a theoretical perspective. So I guess to this audience, I don't need to explain that how machine learning and LLMs in particular has come a long way ahead. We can now solve a lot of math problems, coding. It's also coming up in AR, VR, things like that. So it's everywhere, and we made an awesome amount of progress. Okay. But still, in some sense, we can say we have a lot of way to go. For example, some of the biggest problems people have is these LLMs tend to hallucinate. It's very hard to add new knowledge as world keeps evolving, what to do. So even with all these greatest Gemini models, if you search right now, it can do, even today I just checked this, so give you wrong answers that can water be frozen at 27 or 26. And definitely as over time we are scaling these models, it's becoming more costly. Right? So what should be the way around, how to make it better and more efficient? So maybe we can take a step back and ask the basic question, right? Why are the models first of all growing so large, and every year we're just scaling to bigger and bigger models? So maybe one somewhat simple or explanation in hindsight can seem obvious as our world indeed is so complicated, and if you want the LLM to be good at everything, a lot of different complex tasks, so much knowledge, this and that, we have to make it big. So one way you can do it is as the model increases in size, it can memorize more things. And then there are some theoretical results you can see where they're saying you need memorization for good generalization, especially in the data. So the plot is just showing our language models which are released in GPT-3, and it's just growing. I stopped counting after that. But the main idea is somewhat we are keep increasing the model size to capture more complex parts of the world, more knowledge. Right? But if you think how humans work, right? I don't think we try to memorize everything. We more maybe try to keep around some skills or ability to do, ability to look up information. Right, so we know these important skills, and then once we don't know something, we know, okay, we have to go to Google or this book or somewhere, or ask this other expert on it, and then work properly. So is something similar happening in the LLM space? And yes, of course, people have started doing things. I think many of you might have heard about this, retrieval augmented generation. So nothing new here, but it has been around since 2019 or so. That what you do is when you are given some prompt, right, where is Bermuda Triangle, any question, and then you have some knowledge store. It can be entire internet or can be Wikipedia or whatever your private repository. And based on this query, you can do some retrieval, find some relevant information. This together is given to the predictive model, the generative model, and it can emit the final output. And this kind of like basic framework is popular not just in like text question answer, but also like protein structure prediction. AlphaFold model is actually also something very similar. They do a blast search over known protein structures to the given sequence and make predictions. So very generic and robust architecture, and not just like it gives good quality, it brings a lot of efficiency. So, for example, there's this data set called natural questions, which are basically a subset of some Google search queries about questions. And on this plot, which I'm plotting, is like if we take language models of different sizes. So the blue line is saying parametric only language models of different sizes, and instead of the parametric, I'm just saying how much cost it takes for inference, 1 millisecond, 3 milliseconds for doing like one question. And you can see if you take like a small model or even or the orange to get like a much higher accuracy, and to get something similar you will need like almost like 5x or 7x bigger model. This brings a lot of efficiency if you can design things like that. And moreover, not just for information, maybe in Wikipedia, but it can be also like store other new types of information the model learns during training, stores it, and can leverage some of these efficient data structure. But this is not like only like 5x kind of gap. If you actually think for more like rare questions, especially like natural questions, will have popular things about celebrities and sports and other things which is in the head distribution kind of. So instead of we consider like us academic people, right? So maybe we just created this simple data set of writing bios for researchers, say in CS like NeurIPS conference authors, or in sociology and other journals. Like just take authors from them, and then you want to like ask to write a bio for the researcher. You can create. Most of the researchers have a website. They have decent bios, so you could extract those things. So that's it. So now if we take a model like a Gemini Flash model or a Pro model, and directly like without any retrieval or Google search augmentation, we try to like ask it to generate the bio. So the direct is that Pro, and you can see we are running this AI, which is basically measuring how much of the generated bio is attributable to a source. Right? So higher the better, and these 16 and 20 are like really bad. But if you can augment it with just like one search result, then it goes up pretty large. And I guess nowadays more popular is why only one search. It can be even more like an agentic method. Right? Like you can even do this deep research, which is getting popular, both at OpenAI, Gemini. So you can like first make, given the prompt, like the whole plan, what I need to write, what I need to search. The LLM might give you an option to edit the plan or execute it. It will do like multiple search and retrieve and finally generate. And usually like doing these kind of like agentic RAG or deep research, you can see more uplift in performance. So, and this is like now with a much smaller like a Flash model, you can get what a Pro, like nothing comparable to a direct Pro. And then if you can just imagine how big a parametric only model must be needed to get something like 90s. Right. So the scaling efficiency of such architecture is very interesting. So this is all like the empirical success. So what is our objective? So our objective, at least in this part, we wanted to study framework, like a more theoretical framework, to understand why these retrieval augmented models help. Can we get some just access bound on it, right? So that we can like train this end to end without any explicit supervision of like what retrieval or what tool call I have to do, and can we somehow like highlight what is the role played by the retriever, what is the role played by the predictor or the generator model itself. So can we develop such a theory? And in this talk, I guess we'll go for like two parts basically. Like we'll go to something like very basic machine learning, classical learning setups of like just parametric or KNN or instance-based method. How can we interpolate between them? And then once we have some grasp of when we can retrieve implementation, we will try to develop a training objective to jointly train them. Right? And finally, develop some like excess risk bound showing trade-offs between where the model capacity we can increase and where the efficiency cost will come from. So let's get into it. Yeah, and feel free to ask any question. So classical learning setup, fully parametric. Let's just imagine simple classifier. Some feature vector counts, you run through MLP or any other favorite architecture. Or on the other hand of the spectrum, you can imagine something like KNN classifier or any of these instance-based methods are there. So once the feature vector comes, you have some data store in which you find similar data points to a majority vote and give the output label. And then there's certain like pros and cons. So for example, if you want to update knowledge in KNN, it's like trivial. You just add those new points or delete the old ones, things like that. But the problem is, I guess, it doesn't generalize very well. It suffers from curse of dimensionality, things like that. But whereas these parametric models so far we have seen is like very accurate, scales really good, has some trouble of black box, like it can't explain why things are happening. So can we do something like take best of both worlds, right? And for these two extremes, we have like really good understanding also, right? We know risk bounds for KNN, exactly what cursor dimensionality is, things like that. And even for like some like fixed width MLPs and other things, we understand how things work. But what about something in between? So maybe one thing we can try in between. First thing we can try to generalize is like why only like majority voting, right? So you can think, can we have a slightly more complicated function? Once you do a retrieval, you might want to do maybe distance weighted prediction, right? So instead of just taking a majority vote, you see how far that point is from the others. And then this was the family of this Nadaria-Watson estimators, like classical work, 1980s. Again, we know somewhat learning properties of them. So it's basically taking in your data set whatever points are, weighting it by the distance directly or through some kernel. You can have like a Gaussian kernel or some other kernel on it, but that's the idea. But why stop here? Like you can go slightly more. Like instead of just having this weighted thing, let's just make it a learnable parametric function. A simple parametric function takes as input all the retrievals you have and the input, and then makes the prediction. So this somehow sounds relatively simple model. Like I'm just still talking about classification. I'm doing retrieval. Just instead of voting, I change it to maybe a simple regression there or some parametric model. And then, unfortunately, on the literature side, there's almost nothing studying these. Right? So that was interesting that we don't know much about its learning capabilities, either approximation errors, generalization bounds, things like that. So we wanted to like try to understand how can this help and in which settings can this help, right, for which data distribution. So we'll start with one intuition building example. So suppose it was like few days ago was NeurIPS deadline, and we were like rushing through the paper ready for ICML and NeurIPS submissions, and we have some figure in ticks and we have to fix the alignment, right? And obviously I don't remember the whole ticks manual and what are the commands of moving things, right? So how do we solve this problem? So we usually do is we search on Google or Stack Overflow, find some similar questions which people are saying, look at their answers and adapt it over setting. So this insight can be like transferred to some like formal math so that we can capture that to improve the generalization bounds, right, basically. So so that's exactly like what theoretical framework we can capture it. So one hypothesis we can say is suppose classification on something like this, right? So if you only wanted to learn like one function, you might have to learn this like complicated decision boundary. But if you only look at some local neighborhood, it might be a very simple quadratic or something like that can do the distinction. So maybe the intuition is that once we have like some relevant examples and other things given to us on hand, the problem becomes much simpler and a smaller function class can be able to like solve that or explain it in good accuracy. So you can see like a lot of examples of this also, right? In practice, this in-context learning, why transformer works very well with in-context learning is you give like few examples, 5 or 6 to the transformer, and then give a new test example and suddenly it does much better, right? So it might be like implicitly solving this like local problem which you give few short examples and giving good output. So to capture this, like we try to solve like explicitly a local ERM problem and then see if that the benefit we see in the generalization bound matches with like empirical results. So maybe just for setting up notation and giving some background, right? So you have some labeled data, so distribution, and usually the goal is like given the data you want to learn something from a finite samples, right, from the distribution. And the standard like the F star is like the base optimal kind of given the population distribution, what will be the best function, and there's the empirical risk minimizer is like given this finite samples instead of the full expectation, given this finite sample what is the best F in your function class. And what you want is ideally this gap to be small. So the risk of your empirical versus the population should be small. So only then it means like on unseen regions and other things your prediction will be. And so this like for notation and this goal. So how do we get that local structure? So we think like given some point X, you can think maybe the space is partitioned in some way, and for each point X you can like all these notations are not important, but you have some like ball around which you can have like a local distribution, right? Like distribution just restricted to around that ball, right? And then there will be some probability of how many points are there, especially if there are long tail distributions, not every ball will be populated actually, so there will be some like probabilities on that. And then the assumption is that once you are inside a local neighborhood, like there exists a function class F which is dependent on the data, like the test query point X, and it's much simpler than the overall function complexity. So and still it can like achieve a loss which is or like not much bigger than the global loss if you had this full function family class. So the left hand side is on the local, so expectation is over the local distribution dxr. So inside that ball you can imagine, and the f is from this fx, so a much simpler function class, maybe just a quadratic or some linear thing. So if we just minimize inside that, the loss won't be high compared to like if we found the best f in the whole bigger more complex function class by some factor epsilon. So if this is true, or this is the data structure we are assuming, then if we do something like this local ERM, what it does is once you observe a test instance X, you do some retrieval. So you get some your local nearest neighbors, so that's your neighborhood, that ball. And then inside that ball, using this data, you solve a local risk minimization. Okay? So using this simpler function class flocal, you solve this thing to get a local predictor. And then for using this local predictor on the test example, you make the final prediction. So you can see like now basically at each test time you have to solve this problem, but it's relatively a simple problem. Like you may have like only k nearest neighbors, and then you're solving some simple optimization of that. So you ideally don't need to apply like very big models, so should be cheaper or depends on the settings, but can be cheaper. And something has been inspired by like this local learning done by Leon Bateau and like in 1990s. They were also like thinking about some local learning from another motivation is just like can data on its own like learn, and then we aggregate a more complicated SVM structure, but somewhat similar local learning motivation. So now what do we want? So we want to like take this setup and try to bound its risk. Right? So it means the f of x minus f stars, that gap we want to estimate. And what is more complicated, or what's the new challenge here, is this f hat as the estimator actually now depends on the test instance. So most of the classic literature didn't handle this case. So that was, I think, something new we had to think about when solving this problem. And then the solution went as follows. Right? So we could actually like decompose this risk into like 4 components. So maybe this image can again help guiding what is happening. So there will be like one bound is just how good is our assumption that local structure exists. Then the second term will be like inside that locality, what is the margin, how well data is separated, so on, and how complicated is that local margin itself. Okay? And then finally some like generalization term because of finite sample and coefficient. So this is, I think we broke it down and we had these things. And more concretely, we can like write the main theorem in the paper is that f hat of x, that data dependent risk bound, will have this like approximation error, and the another term which depends on that local complexity, the radiometer complexity of the local function class. And on the plot here, which I'm saying is there's this radius r. How big is my local neighborhood basically? And if on one extreme, if we choose R big enough that all data is encompassed, then you basically will recover back if F locals error on the entire, if you just use that F local class to fit on the entire data set. But then you can see there's some sweet spot, like at some radius you will actually balance off this approximation error, which increases with R, right? Approximation error is measuring how good your F local function class is compared to the entire data. So if you keep increasing your neighborhood, it will be bad and bad. And Rademacher complexity is more on the finite sample setting, that if you, because of finite sample, you could only estimate it locally as bad, And then you had this term NR delta, which we defined earlier, was like inside that ball, how much is the probability there will be points. And we can instantiate it particularly for linear networks, if that F was a linear network, or if it was an MLP with Q max width, things like that. And you can get terms like this, but in the order it's basically the same. So, any questions here?
One question.
Yes.
The radius part that you consider in this mathematical setup, what is the constraint on R? It is based on this input cell or the estimator error. Because there's a literature on the statistical learning that, for example, some researchers actually did consider, instead of the, for example, universal Rademacher complexity, they used the local Rademacher complexity on the variance of the estimator error. So they bound the space. So I want to see the distinction between those.
Yeah. So I think the gap. So it's, I think, slightly different setup. So the paper, I guess you're talking about is Satyan Kale and others doing this local Rademacher complexity, but they were again like not bounding this like f hat x. They were just bounding global f of x and then using that local Rademacher to get like a tighter bound. Versus what we are trying to say is if you actually like, this is the empirical problem we solve, we can get we can like explain basically why this retrieval augmentation is helping, which their theory will not suggest that. And then till now we had to do this like very explicit construction, and in practice we'll have like something like a transformer, right? So we won't be running this local ERM explicitly. So just for completeness, what we can do to make the theorems work for such black box models is consider all this like retrieved points as like some extended feature space, and then in this extended feature space you can create like a local distribution and a kernel, well-defined kernel on it, using which you can get something similar generalization bound, and it depends on the same terms, so it can capture that. So it's in the paper, but I'm skipping it. So now let's look at some experiments for this. So just synthetic data, some binary classification task I want to do, and we compare like these different function classes, like linear, some polynomial, a radial basis function, some MLP, scale, and others. And then we add on the right side like retrieval plus those function classes. And on the plot now, which you have seen, is number of neighbors we retrieve. And the dash line is like when basically no retrieval is happening, or basic number of retrieval is 0. So you can see if the function class is too simple, right, like linear or other things, the accuracy is basically random. It cannot explain this more complicated decision model. But linear plus retrieve already is doing like so well. So it's this blue curve going up and down. So with the right tuning of the neighborhood, you can see at the sweet spot. And that's somewhat like very similar to the theoretical curve we saw. So there it was the loss, so the risk, so it looks like the U. Here it's the accuracy, so it's inverted, but it's similar. So we also had a line for transformer and retrieval, but for this very simple case, the transformer alone could solve everything, so retrieval didn't do much. So it's basically that gray line on the top, almost flat. Yes.
So what is the performance of like only retrieve?
KNN classifier.
Oh, KNN.
So you can see it can do better. So you are better than just simple majority voting. So this parametric function gives you some more expressive power.
So here in this case, I guess the retrieval part is much more powerful than the...
Yeah, the retrieval plus the small linear or polynomial on top of it makes you
Because KNN itself is already good.
KNN is good, but it's like 80% max, right? Versus we can go to 90.
80. Some color.
Yeah, the yellow one.
Oh.
And then we can do something similar with more real data, like say CFAR, you want to do cat versus dog. And you can see like the similar trend, just the plots are now a lot more noisy with data. Okay, so I think this part we are trying to see like, yeah, how can we go between parametric and instant-based models. We set up a theoretical framework, and we can see like when retrieval helps, right? We had this sweet spot where it increases and goes down. Okay, so recall that we were assuming some existence of structure like this, but the problem is in real data this might not exist naturally. Right? So, for example, if you had image data and you were only looking at like pixel distance, maybe irrelevant photos will be actually similar to each other. Maybe a plane and a bird, or a squirrel and a sparrow will look similar in pixel space, but that's not what we actually want. Right? So ideally, you want to like learn also like an embedding space, such that in that space, this beautiful structure is like revealed more clearly. Right? So you want like a retriever or an embedding model which exposes this, and then the parametric model can do a combination or some more processing on top of it. So now basically retrieval augmented model like fully should be, there should be a predictor, there should be a retriever which maps it in some embedding space of which you do the retrieval. Just formally we are capturing. And for simplicity, just assume we do one retrieval instead of k. And H of psi is basically the LLM generation or classifier, whichever, and retriever is R theta. And then the retriever induces like a probability distribution over your entire data store, because it gives a score for every pair of query and data, and then you can use that with a softmax to get distribution over entire data store. And something similar to previous setting, like you'll be given a fixed data training source, xi, yi, sn, that of fixed size. That data store can be again like that Wikipedia, can be in context example, whatever. And similarly, we measure quality by estimating its risk. So it's a loss now across both the retriever and the predictor. So that one more expectation where you have a sample over the retrieval itself. So that's an addition. So like continuing our previous kind of experiments, right? So now if we had like an ImageNet data set, and for ImageNet data set there are a lot of retrievers available. Like Align is, for example, some retriever or embedding pretty good available. So if you use that plus a very small like mobile net kind of CNN, you can see like you can almost reach the performance of as good as a much bigger model. So you are getting like almost 5% boost up, and usually that means like in ImageNet is pretty compared, so every percent like the model size grows pretty fast. So you could have, we could like boost up 5%, which is pretty significant. But moving forward, what happens is often like we won't be in this world where its ImageNet is the data set and a retriever is available for us. Right? So most of the time we won't have like a good retriever for our task. So we will only have like end. It is the input, it is the final supervision, it is the final answer I want. So we want some way to have like an end-to-end training. And one key idea is, can we use the predictor to guide and train the retriever on the fly also? So basically what example should I see such that my prediction becomes easier, right? So it can like force some kind of like regularity structure on the retriever to learn. and you can just do it very simply, like just take the risk and replace it with empirical version. So instead of expectation or distribution, you have sum over data set and sum over the data store, the index from which we retrieve instead of that expectation. And if you take like a log loss, so that loss of h of psi can just become like log probability or say prediction of the answer, right? And then this is your final objective between. So there are still some concerns like summation over p, right? That is too expensive. So we can try to approximate it with maybe log k, or try to solve this with policy gradient or some reinforcement learning kind of method, because that expectation is over. So we want to like maximize over a sampling process, so something like policy gradient can work. So just connections with some popular methods in this end-to-end training. So this was the top line is our objective, and then there are these papers like EMDR2, which were trying to propose a joint prediction, but they didn't have like a theoretical framework or why it should be a good objective. But you can see it like they came up with something very similar. The difference is some of the log term was outside, and you can use like Jensen's inequality and say that like our objective is actually an upper bound on that. So if we are minimizing ours, their objective is also getting minimized. So we also try to solve that problem implicitly. Then there was this other work called like Atlas, which got some of state-of-the-art results on these retrieval augmented models, and they had this kind of interesting loss. And again, you can see some like similarity or contrast with us. So the top line is our loss again. We just wrote it in terms of cross entropy to match the notations or make it simpler to understand. So ours is a cross entropy between the retriever scores. So the first one is the retriever score, and the feedback from the predictor model on how good is that retrieval to get my answer out. Right? So this match between the cross entropy between those two distributions. And as you know, cross entropy is not a symmetric function. So Atlas did somewhat like the reverse. So they are saying like, okay, we take the predictor networks, normalize them to form a probability distribution, and do CE with the retriever scores. So the forward versus reverse CE usually has like this mean versus mode seeking behavior. So if you try to say in this toy example on the right side on the plot, right? So we are trying to like always learn this function Q, and P in the blue is say the true given or fixed probability distribution, and we are optimizing Q, right? So R mean of cross entropy PQ or QP. And they will try to learn different distributions. So the forward one will try to learn the mean or like full coverage of the space, versus the reverse scale usually learns the mode, only one mode. So because of that, the speed is can like suffer from like exploration problems. So it once finds some reasonable paragraph or some information source and it will get stuck to that. Whereas this one can have like a much better exploration output. And similarly, this like RLHF and RLAIF is very popular these days, and this method can be seen as like also on that same vein, and you can use most of the tools from there. So the retrieval part is basically a policy, so that's why you can use policy gradient. And reward, instead of having a separate reward model, the generator which is predicting the answer is itself the reward model for that loss. And but this time we are like training both the retriever and the reward model itself jointly, which RLAIF or HF usually don't do. So finally, we can go through the risk for these. So again, like similar to previous setting, you want to estimate what is the gap right between these two. So something similar, we'll decompose it. Don't bother looking at this theorem, it's just there. But I'll show you some like plots what this looks, so especially for MLPs. So once we specialize it to MLPs, right? So MLPs, L pred and L rate is number of layers in the retriever and number of layers in the predictor model. And this plot on the left side is showing basically the accuracy or the risk. And you're seeing like it's in between, there's a dark spot. Maybe in the projector it's not very clear, but on the upper right side there's a dark spot. So it means just blindly increasing L pred alone is not as good. There's some like balance between them in which you can get the best risk. Right. And on the right hand side plot, what we are seeing is the dash line is saying if you had only the predictor model, no retriever, what would have been your risk? And then adding this extra information source, we could see that the risk actually went down. Right? So once the index size is big enough, it means like it has enough content with some probability you will hit them, which is relevant. Right? And then as the index size keeps growing, like you will see better performance, and or if your number of data increases, you see better gain by using this retrieval augmentation. And just like empirically, here you just take like natural questions, so you take like models of like different size for retriever and predictor, and you can see something like the largest value, like the large is almost same as like maybe a small and large. And similarly on trivia QA and so on. So from the efficiency perspective, maybe one thing we can know is earlier table was only showing the accuracy, right, in terms of exact match. But if you look at like query per second we are processing, so based on the predictor size is very much dominating how much the overall time it will take. The query or retrieval part is very small. And so if you want to say achieve some performance say around 40 accuracy, right? So it seems like if you did like a small model with a very strong retriever, that will give you most bang for buck because that query per second is much larger. So that's why like when we are designing practical systems, we should try to see where we should put the capacity to get maximum bang for buck. Yeah, with that I would like to like conclude the talk. So we saw like how this retrieval augmentation in the community already is well known that it's a very effective method. We proposed like a theoretical framework to understand it. On the way we had to make some new tools on interpolating between these like extremes of parametric fully or instance-based methods, proposed a joint learning framework, and then there are many more exciting opportunities to do next, especially this agentic methods which I showed earlier, like deep research. Can we extend the theory to that? Yeah. Thank you.
Are there any questions from the audience? So I have a question. So because like in context learning is about like during test time when you feed a sample, you were just kind of doing some implicit maybe gradient descent steps. How is, or do you think your framework is related to that in the sense that maybe you assume that during the retrieval step you're doing some local learning? Like maybe is it possible to use this framework to explain maybe to some extent in context?
Yeah, so I think I mentioned that. So once you retrieve those examples, so the transformer implicitly might be doing that local learning which I was showing, right? So yeah, so that's why that benefit which we see from few short examples, this is like capturing that.
Okay, so basically that's a direct.
Yeah, direct consequence. Yeah, because it's the same model. I didn't change anything. The input output, like if I give X plus augmented with few short, the improvement happens, and that's what it's saying.
Yeah,
and also you can see if you actually do too much few shot, it actually degrades performance. so that you get that full curve.
So that also aligns with what people observe.
I'm curious about this RL, AIF, and the HF part. How do you precisely evaluate the quality of retrieved answers? For example, by employing a model to give you such a reward, what is the underlying assumption that such a model knows why this specific retrieved result is good or not?
So ideally it should be some verifiable or whatever reward function given to us, right? Loss function we assume was given to us, but if it's also a reward, we're just assuming it's good for us. But that's I think an open problem in how it needs to be done. Maybe when we go towards more this agentic understanding framework, we can explore that more. In that, can it go and re-verify things that does it, even if reward signal model says good, am I reward hacking or doing something like that? You can explore there.
Another question is regarding this joint learning. What is the unique advantage of jointly training both models? Is that some transfer learning assumption where multitask learning such that they are mutually beneficial to jointly train?
Yes, I think it's mutually beneficial because if you just have a generic retriever, right? So we are saying if you have some fixed retriever and you only train predictor, you definitely get improvements. But maybe the predictor is not leveraging the best way the retriever is not leveraging the best way to give data to the predictor. Right? Predictor might want these 5 things so that it can answer question correctly. So now if you do joint, it can train the retriever to find me these examples instead of a generic. These are the 5 relevant things here. So that's why you can see the numbers quite go down. So this one, for example, is where we are jointly training, and it goes from 23 to 30 for even small models. Yeah.
Thanks.
Let's thank the speaker.